So let's look at this example, folks, continuing on with the idea of linear transformations. So let's define D, which is going to map from C1 space to C0 space, be the differential operator. So again, this is a little bit frustrating because we're now thinking of things like integrals and derivatives as mappings of functions to different functions. So take any function who is differentiable and whose first derivative is continuous and map it to the space of continuous functions by taking the derivative. Well, then my claim is that this is a linear transformation. Let's go ahead and see how we prove that. Well, let's let f and g be elements of the space of continuously differentiable functions. And now let's go ahead and apply the differential operator to f plus g. Well, the differential operator is what we think of when we say take the derivative. So we're going to take the derivative of f of x plus g of x. And again, this is one part that's a little bit frustrating. Somewhere in a calculus class, you proved that this derivative operation is linear. So I could rewrite this as df dx plus dg dx, which is the same thing as taking the derivative of f plus the derivative of g. So I'm not saying anything that you haven't learned before, but instead what we're doing is we're thinking of this as mapping from one function space to another. We took a sum of two functions inside C1 and showed that that could be the same thing as the sum of two functions inside C0. So we've just proved the first requirement to show that this is a linear transformation. The second thing we need to do is let's pick just some real value a, and let's look at the differential operator applied to a times f through regular multiplication of function, multiplication of functions by say scalar. So this is equal to the derivative of a times f of x. But what did we learn in one variable calculus? That derivatives behave linearly in this regard, so we can factor the a out. So that leaves us with a of d dx of f of x. But that is simply a times our differential operator applied to f. So this step with this step shows that D is a linear transformation. And we could repeat this. For example, those of you who have done Calc 3, you've learned about the dot product. Well, if I think of V as some vector that I'm going to hold constant, then I could apply the dot product on the by V on the right to any function, or excuse me, to any vector u, and this behaves linearly by the properties of dot products. Okay. So here I say the point that I've made a few times, that improving the above transformations are linear. We're simply utilizing the linear properties that we've proven in earlier classes. The other thing is that the terms linear transformation and linear operator are sometimes used interchangeably. And for simplicity, I'm only calling these objects linear transformations, even when the term linear operator may be more precise. Okay. So we've seen several examples of things that are linear transformations. Let's look at something that's not. So here I've got a mapping that's going to take real values to real values by the square root function. Okay? I claim that this is not a linear transformation. Why? Well, if I were to, let's pick a and b in the real number system, meaning in this first space here, if I take s of a plus b, that's equal to the square root of a plus b. The thing is, s of a plus s of b, the thing that we're hoping to show that it's equivalent to via the linearity, would be the square root of a plus the square root of b, and these two expressions here are not equal in general. That's enough to show that S is not a linear transformation. We could take that a step further, or if we pick, let's use alpha, I guess, be some real constant. If I took S of that real constant times, let's take it times B, just so the letters don't get too confusing, this does not equal alpha times S of B. What do I mean by that? Well, if here is B is say 4 and alpha is 3, if I said take S of 3 times 4, that would be the square root of 3 times 4, which is equal to the square root of 12. But if I were to take 3 times s of 4, that would be equal to 3 times the square root of 4, which is equal to 3 times 2, or 6, and these two quantities are not equal. So the square root operator is basically as nonlinear as you can get, because it doesn't distribute over the sum of operation inside the real numbers, nor does it distribute over what we're thinking of as scalar multiplication. All right, so now I'm going to go ahead and pause the video here, because this is the linear operator we've been building to for this